Okay, so today we're going to be talking about generating functions. Everyone can hear me, right? Um, so first of all, let's go over what a generating function is. So a generating function is basically a polynomial, let's call it p of x, that stores information about some type of sequence. For example, it could be something like 1 plus x squared. And what this means is that we have some number that we don't know anything of, or we have some number y, and the number of ways it can be 0 is one way, and the number of ways it can be 1 is also 1, and the number of ways it can be 2 is 1. And you may be wondering, where did I get these numbers from? Well, if you look at the polynomial as a sum of a of I times x of I, so like in the case of our polynomial 1 plus x squared, a of 0 would be 1, a of 1 is 1 as well, and a of 2 equals 1. A of i's are just like the coefficients of the polynomials. Wait, how do I let someone in? Okay, there we go. So like AI would be the number of ways, a number of ways, y, or some number, I'm just going to call it y, can be I. So for example, for this generating function, there's exactly one way for this number to be 0. We have one way for this number to be 1, and we have one way for this number to be 2. To make this more concrete, let's go over some real-world examples. So if you have a dice, right, what a dice can do is that it has numbers 1 through 6, right? And it can get each of these numbers exactly one way, right? If you roll a dice, there's exactly one way to get each of the numbers 1 to 6. So the generating function would look like x plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th. I think this should be clear, right? And it may not be apparent why generating functions are useful at this point, right? Because we found a way to encode some type of information in a polynomial, p of x, right? But we don't actually know exactly how to use it. So one of the main uses of generating functions is that if you add to if you supposedly do some generating function twice, as in you roll a dice twice, right? If you roll a dice twice, and then you add the numbers, then how do you compute this? How do you compute the number of ways to get some number like 7 or something, right? So if you just write out your table, if you find the number of ways to do everything, so you would have exactly one way to do 2, 2 ways to do 3, right? Because you have 1 and 2, and 4 ways to do 3 ways to do 4, all the way to, I believe, you get 6 ways to do 7. And then you keep on going down until you hit 12, in which case there's only one way to get a sum of 12 when you roll 2 dice. Well, if you notice that this is just the product of the two generating functions, right? So in this case, it would be x plus x squared plus x cubed plus x to the 4th plus x to the 5th plus x to the 6th squared, right? You can actually check this yourself, but this is a bit more of a complicated example. I guess a simpler example would be a coin, right? So what does a coin do? So a coin lands heads with probability 1/2 and tails with probability 1/2 as well, right? So in generating functions terms, if we only care about the number of heads, then the generating function for the coin would be 1/2 plus x over 2, right? because you have a 1/2 chance of getting no heads, right? Tails, or 1 head. And if you remember from before, if we flip 2 coins and we add up the number of heads, that's the same way as multiplying the generating functions. So if we have our 2 coins, 1 plus x all over 2, and we square this, right, then what we get is 1 over 4 plus x over 2 plus x squared over 4. And this makes sense, right? Because if you flip a coin, you have a 1/4 chance of getting both tails, you have a 1/4 chance of getting both heads, and you have a 1/2 chance of getting 1 head and 1 tail, right? So this is where the usefulness of generating functions really come into play. It's if you do like something twice and then you add the values, it's the same way. It's the same thing as multiplying the generating functions together. Okay, so let's look at some more examples. So for example, if you have only pennies, this is like a trivial example. So if you have only pennies, how many ways to pay n cents? Well, there's only one way, right? So the generating function would be 1 plus x squared plus x cubed all the way to plus infinity. But let's say you have, and if you this is not that important, but if you're comfortable with infinite series, this actually equals 1 over 1 minus x, right? Don't be too worried about like when the sequence like converges or diverges, but if you multiply both sides by 1 over 1 minus x, then you should get equality, right, when x is less than 1. But this is generating functions, so like I wouldn't worry too much about polynomials. Anyways, some more. So that wasn't that useful, but what if you have 1 cent coins and 2 cent coins? Well, what you can do is you can multiply our two generating functions, right? So first of all, let's look at the ways for doing 2 cent coins. So 2 cent coins you can do exactly one way when what you want to pay is an even number of cents, and you can do 0 ways when you want to pay an odd number of cents, right? So for example, 2 cents would be 1 plus x squared plus x to the 4th plus x to the 6th all the way to infinity. And 1 cent would be 1 plus x squared plus x cubed all the way to infinity, right? So if you multiply these two generating functions, then you can find exactly how many ways you can pay with 1 cent and 2 cent coins. Of course, you don't want to multiply infinite functions. So one thing you could do is just look at, if you want to pay n cents, then you only consider like the numbers that are less than n, right? Okay, so let me see, what other examples are there? Okay, I think we can go over some examples, like some problems now. So I believe this is an old HMMT problem, like a HMMT team or something problem, or was it an ARMO problem? I don't remember. Anyway, so it says that you have 2 dice, right? So if you have 2 dice and you roll them together, and you get sum of numbers on both dice. And you get 2 ways, or sorry, you get 1 way to get 2, you get 2 ways to get 3, all the way to 6 ways to get 7, and all the way to 1 way to get 12, right? So the question asks, can you can you construct two other dice? They may not be equal, that have the same, such that when you roll the two dice and then you add them together, you get the same thing as this, right? So in other words, if you have some like D1 and you have some dice 2, then if you roll these two dice and, like, let's say you get x here and y, then your number would be x plus y, and you want the number of ways to get each number to be the exact same as if you rolled two regular 6-sided dice, right? So that means that the generating functions of d1, let's call this d1 of x times d2 of x, equals 1 plus x plus, or sorry, there's no 1. It's just x plus all the way to x to the 6th squared, right? Everyone's fine with that, right? Okay. Now, but of course we don't want d1 and d2 to be, oh yeah, the problem also says that d1 and d2 are not regular dice. So you want to find d1 and d2 to be something else. So now that we have formulated this problem in terms of polynomials and generating functions, like the most obvious solution path would just be to factor this guy, right? We want to find two factors that can give us a valid choice of d1 and d2. So first of all, 1x plus x squared plus all the way to plus x to the 6th. This has exactly 6 terms, right? And they're all consecutive. So that means that x plus 1 is obviously a factor, right? So if you factor this, it becomes x times x plus 1 plus x to the 4th plus x squared plus 1. So what you get is that d1 of x times d2 of x equals x squared times 1 plus x squared times x to the 4th plus x squared plus 1 squared. So now we want the degrees of d1 and d2 to be 6, right? We want d1 and d2 to have the same degrees. So one way we could have d1 is d1 equals x squared times x to the 4th plus x squared plus 1, and d2 to be, I believe, 1 plus x squared times x to the 4th plus x squared plus 1. Wait, this may not actually work. Right. Hold on. So this would be x to the 6th plus x to the 4th plus x squared. Wait, hold on. Let me think about this. Wait, I think you want... Wait, no, I think you want x... Right, never mind. I think you want... I think you want, wait, no, I think this works anyways. So this would be x to the 6th plus x to the 4th plus x squared. And then you can find whatever d2 turns out to be. And if you like have these two dice together, then if you roll them both, you should be able to get, and then you roll them both, and then you add the two numbers. Then the number of ways to get each number is the exact same as the number of ways to get as if you rolled two regular dice. Okay. Let's see what else. So another useful thing about generating functions is that you can actually let me see. Okay, so let's say you had, you may remember from math counts, like what the chicken McNugget theorem was. So if you have if you have A cent coins, right, and you have B cent coins, then what is the largest, largest amount you can't pay for? Right, so we want to find the largest amount that you cannot pay for. And some of you may have just remembered the formula AB minus A minus B, right? So if you write it in terms of generating functions, what you have is 1 plus x to the a plus x to the 2a. Oh yeah, it's fine if you don't know this, but so like this may be useful later. If you have A cent coins and you have B cent coins, then the largest amount you cannot pay for is AB minus A minus B. So what this really means is that if you have only A cent and B cent coins, you cannot pay for AB minus A minus B coins, right? But you can pay for any coins above, you can pay for any number of coins that's above this number, right? So if you had something like AB minus A minus B plus K, then you can always pay for this. You can always pay for this. And that's actually kind of it's kind of a useful theorem. It shows up a lot in math counts. Hold on. Let me just check this one thing. Okay. And if you form this in terms of generating functions, you have 1 plus x to the b plus x to the 2b plus all the way to infinity, right? So basically, what do we want to do? We want to find the largest I such that there is no x to the I term, right? This basically means that there are 0 ways to pay for I cents. Right. Okay, so now we want to find this I, and I believe the easiest way would be just to kind of bound the number of terms. Wait, hold on. Hold on. Okay. Okay, never mind. Okay, so oops. So first of all, if you look at wait, hold on. Okay, so I think you may have to. Okay, I think this may actually be a bit more complicated than I thought. Anyway, so another way to write this would be 1 minus x to the a, right? So if you remember from before, 1 plus x squared plus all the way to infinity equals 1 over 1 minus x, right? So this actually would be 1 over 1 minus x to the a, and the b cent coins would be 1 minus x to the b. So what you would get would be 1 over 1 minus x to the a minus x to the b plus x to the a plus b, right? We just multiplied the bottoms. And what this means is that so if you look at the what this means is that if you take things wait, hold on. What this means is that if you look at the ath, or if you look at the term x to the a plus I and the term x to the b plus I, then if you add these two guys, then it's the same as adding the coefficients of x to the I and x to the I plus a plus b. Wait, hold on. I just need to hold on. I'm sorry. I just need to check this one thing. Okay, anyways, so then I think we can just look at mod stuff. So if you look at mod A, right, well, the smallest value that, if you take everything mod A, then what is A, so like B, if you have like KB terms, then you have BK mod A, right? So if the number of terms is BK mod A, then, if you have KB terms, then the total number of cents that we have is B times K mod A, right? Because terms that are A cent coins do not affect the number of cents mod A. And of course, if you have, the hardest to get residue would be negative B, right? Because we can get 0 mod A very easily, we can get B mod A very easily, and we can get 2B pretty easily as well. And the hardest to get would be minus B mod A, right? Everybody kind of sees this, right? And in other words, this would be A minus 1 B mod A. Whoops. Hold on, I just need to. Wait, let me see. Hold on, let me just find this. There you go. Okay, my bad. I think this problem was actually kind of hard to solve with generating functions, so I'll just do it the normal way. My bad. Anyways, so if you notice, negative B mod A is kind of hard to get, right? And by the same token, negative A mod B is also hard to get. Because to get negative B mod A, then you would need at least A minus 1 coins size B, right? So now we basically want something that's negative B mod A and negative A mod B, and that is AB minus A minus B. And if we need at least A a minus 1 coins of size b, then what you would need is a minus 1 times b plus b minus 1 times a is 2ab minus a minus b. So obviously we cannot get ab minus a minus b coins. Okay, let's see. What are some other good examples? Okay, so here's a fun example. So let's say we have something like an anti-penny. So an anti-penny would be kind of like the opposite of a penny. So a penny would be when you flip a penny, you either get 1 heads or 0 heads, right? So it would be 1 plus x over 2. An anti-penny would be you either get nothing or you get negative 1 heads. So for example, you would get it would be 1 plus x to the negative 1 over 2. And what happens if you have n pennies and n anti-pennies? So first of all, what would the generating functions look like? Oh yeah, so to clarify, we would flip all n pennies and all n anti-pennies, and we would add the number of heads together. And remember, an anti-penny either has 0 heads or negative 1 heads, each with probability 1/2. So what it would look like would be 1 over 2 to the 2n, or I shouldn't go that far actually. 1 plus x over 2 to the n times 1 plus x to the negative 1 over 2 to the n, right? And 1 plus x to the negative 1, this is 1 plus 1 over x, equals 1 plus x over x, right? So in total, this would be 1 plus x to the 2n over 2 to the 2n times x to the n, right? So from here, we can actually use the binomial theorem, right? Because you can find the expansion of 1 plus x to the 2n. So if we want to get I pennies, and I can be negative actually, then in this case, we would get the number, or like the probability actually of I pennies would be 1 over 2 to the 2n times. So in here we have to be careful because we have an x to the n at the bottom, right? So that really shifts all the terms over by n. So we're actually looking at the I plus nth term of the expansion 1 plus x to the 2n, right? So in this case, it would be x to the n plus I over x to the n times 2n choose n plus I. And of course, the n's cancel out, so we get the x plus I term. So the probability of I pennies would be 1 over 2 to the n times 2n choose n plus I. Oops. Let's see, what other examples? It seems like I can't make any more frames, so I think I have to create another board. Let me do this really quick. Okay, okay, so I guess this is kind of a fun example as well. So you have you in this country, let's call it country X. You only have coins that are of size powers of 2. So you have a 1-cent coin, you have a 2-cent coin, you have a 4-cent coin, 8-cent coin, all the way on, right? All the way to infinity, right? And you want to okay, wait, this may not be the best. Okay, whatever. You have coins that are only powers of 2, and you can only pay with at most one coin of each type. So how many ways are there to pay, how many ways to pay n cents? Well, if you know, this is just base 2, right? So the answer is just 1, right? But if you think about this in terms of generating functions, oh yeah, can you see this? This is a 1. I wrote a 1 down here. I don't know if you can see this. If you write this in terms of generating functions, right? So on one hand, we have exactly one way to pay for everything. So it would be 1 plus x squared plus x cubed plus all the way to infinity, and this equals 1 over 1 minus x, right? On the other hand, we have 1 plus x times 1 plus x squared times 1 plus x fourth, all the way to infinity, right? And this is interesting because we actually have this identity, right? So if you multiply 1 plus x to the 2 to the k, and then you multiply all of these guys, this actually equals 1 plus x squared plus all the way to infinity. I think this may come up later in a different problem. Okay, let's see. Okay. Let's see if we can find. Okay, let's look at this example. So let's say if we wanted to find the generating functions of the Fibonacci numbers. So I guess this would be a little bit more abstract, as in what we want is f of 0 plus f of 1 x plus f of 2 x squared plus f sub 3 x cubed all the way to infinity, right? So f of I is just the ith Fibonacci number. And basically, we want to find what this is, right? And of course we want to use the fact that f of n equals f of n minus 1 plus f of n minus 2. For those of you who aren't familiar with Fibonacci numbers, the Fibonacci numbers are just numbers where the nth number is the sum of the previous two numbers, right? And that's really just what a Fibonacci number is. And if you remember from the generating functions, okay, so first of all, remember if you remember the example where we had like 1 plus x squared plus x cubed plus to infinity equals 1 over 1 minus x. Basically what happens, the way we found this was if you multiply both sides by 1 minus x, then what you get is 1 equals 1 minus x to the 1 minus x to the infinity, right? But x to the infinity doesn't really exist, so this just cancels out and it just becomes 1 equals 1. So we would get this equals 1 over 1 minus x. And now we want a similar canceling thing to work out for the Fibonacci numbers, right? So if you have f0 plus f of 1x plus f of 2x plus to infinity, you want to multiply this by something such that everything cancels out. And this something that we want to multiply by is 1 minus x squared, right? Because if you think about it, this becomes like if you look at well, first of all, it would be f of 0. Or first of all, let's look at the x to the I term, right? So the x to the I term, the coefficient of x to the I would be f of I, right? Because you multiplied it by 1. So like, let's put our f of I, x to the I here. We have, wait, let me draw a clear diagram. So we want to find the x to the I term, right? And we have our Fibonacci sequence here. So f of 0 plus f of 1x plus, and we want to find our x to the ith term, so we have our f of I minus 2 x I minus 2 plus f of I minus 1 x I minus 1 plus f of I xi to infinity, and we multiply this by 1 minus x squared. So the x to the I term would be, first of all, let me see, can I change colors? Yes, I can. So it would be 1 times f of I xi, right? So we would get f of I here. And if we multiply negative x to this guy, we would get minus f of I minus 1. And negative x squared to this term, we would get minus f of I minus 2, which equals 0. And now we have that every single term evaluates to 0 except x to the 0 term equals 0, right? X to the 0 term equals to 1. So we have that this whole expression here, this whole expression equals 1. So what does this mean? This means that f0 plus f1x plus f2x squared to infinity equals 1 over 1 minus x squared. Now let's see some like another useful thing about generating functions is that we can actually use properties of the polynomial to prove some nice things. And I'll show you what I mean by that in the next example. So I think this was actually an HMMT problem at the end. Oh yeah, if you have a problem suggestion, you can just type it in the chat, and I'll do my best to just like answer it. So like let's say you have coins of probability 1 over 4, 1 over 6th, and 1 over 2 to the n of landing heads, right? These are all coins, by the way. So for example, this coin has a 1/4 chance of, so like this is the probability for heads. Heads of 1/4 and 3 over 4 chance is tails, right? And this would be, heads would be 1 over 6 and tails would be 5 over 6. The way a lot of people did this the way that you could do this is just engineers induct, right? So if you have 1/4, then obviously it's just 1/4. Oh yeah, sorry, my bad. I should say the problem statement first of all. So the problem statement is, what is the probability of even number of heads? And one way to do this is engineers induct, right? So we have the coins 1 over 4th, 1 over 6 to all the way to 1 over 2n, and the answer should be something in terms of n. So if we list out the first few terms, we should be able to kind of guess what the answer is, right? And then hopefully just induct from there. But I'll show you like a much easier way to do this problem. So first of all, let's write out the generating function. So the generating function would be 3 plus x over 4 times over 5 plus x over 6 times 7 plus x over 8 to 2n minus 1 plus x over 2n. And let's call this p of x. Right, and we want to use, besides just brute forcing it, we want to somehow find what this p of x should be. So first of all, let's say what our end goal is, right? End goal. If p of x equals sum of ai times x to the I, then we want a0 plus a2, and of course x to the I, wait, my bad, it should be x to the I. X to the I, so sorry, a to the I, a sub I is the number of ways for, sorry, not the number of ways, it's the probability I heads, right? And what we want is we want the sum of all A even, right? So we want A0 plus A2 plus A4 plus A6 and so on, because we want an even number of heads. And if you know your polynomial tricks, what this really is P of 1 plus P of negative 1 over 2, right? Because if you have some sort of polynomial a of x, x to the I, then P of 1 equals the sum of a to the I, and P of negative 1 equals, so it would be the sum of a sub 2 to the I minus the sum of a sub 2 to the I minus 1, right? Because all the even terms, x to the even equals 1, and x to the odd equals negative 1, right? So if you add these together and then you divide by 2, well, the odd terms are counted 0 times because they're added in the P of 1 term and they're subtracted in the P of negative 1 term, right? But the even terms, they are actually counted twice. So after you divide by 2, you get exactly what you want. You get a of 0 plus a2 plus, there shouldn't be a sum here, my bad, plus a fourth to infinity, right? So now, we can actually, let's see if we can actually calculate P of 1 and P of negative 1, right? So first of all, let's look at P of 1. P of x equals 3 plus x over 4 times 5 plus x over 6 all the way to 2n minus 1 plus x over 2 to the n. If we plug in x equals 1, right? Well, each of these terms equals 1. So P of 1 equals 1, right? And let's look at P of negative 1. P of negative 1, well, let's look at the what each term is. So this term becomes 2 over 4 times 4 over 6. And if you keep on going, it would be 6 over 8 all the way to 2n minus 2 over 2n. And what you notice is that this telescopes. The 4 cancels out, the 6 is canceled out, the 8 and everything, all of this cancels out, and what you get is 1 over n. And remember, our answer is P of 1 plus P of negative 1 over 2, which equals over 2, 1 plus 1 over n equals n plus 1 over 2n. And this is our answer. That may have seemed like it took a long time, but once you're more familiar with generating functions, you should be able to see this very quickly and just be able to do this solution very quickly, right? You should just be able to notice that you want to find P of 1 plus P of negative 1 over 2, and you should plug in 1 and negative 1 and see that you can actually evaluate these two numbers very easily. Okay, let's see. Let's look at another example. Okay, so generating functions is really where we get this concept of root of unity filter. I don't know if you guys are that familiar with this, so we don't have that much time left, so I'll go over this kind of quickly. Root of unity filter. So basically what a root of unity filter does is you like input some sort of complex number such as I, and then you evaluate the generating function such that it like kind of some terms kind of cancel out, and we'll see what I mean by that. So if you look at P of 1 plus P of negative 1 over 2, this is the most basic form of root of unity filter, right? Because this basically cancels out the odd terms and leaves you only with the even terms. But what if we want only terms multiple of 4? Right? then it gets a little bit harder, right? Because you can't just use 1 and -1, right? You need to be a little bit more smarter, right? So, for example, if you have something like p of x equals sum of a sub I x to the I, where I goes from 0 to infinity, and you want to find a sub 0 plus a sub 4 plus a sub 8 to infinity, well, you would need some way to cancel out all the terms that are not multiples of 4, right? And the way we do this is, of course, we have our x equals 1, right? P of 1 equals a0 plus a1 plus a2 plus a3 and so on, right? And we have our x equals -1, and p of -1 equals a0 minus a1 plus a2 minus a3 and so on. But we want something else that lets us also separate out the terms that are multiples of 4. And what we do here is we look at x is a root of unity, and in this case it would be the 4th root of unity. If you're not really familiar with roots of unity, it's not that important. Basically, a root of unity is a complex number. If you're not familiar with complex numbers, I think that's okay too. For this example, you don't actually need too much of an understanding of complex numbers. Just like keep that in mind. So a root of unity is something that's like w, where w is a complex number such that w to the k equals 1, right? So in general, if we want every kth term, we want kth root of unity. And of course, a kth root of unity is just something such that when you take it to the kth power, it brings you back to 1. So 1 is always a kth root of unity. If k is even, then -1 would be a kth root of unity. Here, we're concerned about 4th roots of unity, right? So if we have something like w to the 4th equals 1, then what we really want is something that's like w squared equals 1 or -1. And of course, if you know some basic complex numbers, w equals 1, -1 obviously, I or -I, right? So this motivates us to plug in I, right? So what happens if we plug in p of I? And of course, maybe p of -I. Well, this becomes a0 plus I times a1 minus a2 minus I a3, and it repeats from there, right? P of -I equals a0 minus I ai plus a2 plus I a3 to infinity. Right, so this is pretty useful. I would say that the most and then now of course and now of course we want to find what all these things are, right? And what you notice is that if you I think if you not add, but you want to subtract, this is my bad, this is minus as well. So now you want to somehow add or multiply these things to get only the every 4th term, right? And one way to do this is just to add everything up, right? So if you look at all these terms, if you add everything, and then divide by 4, p of 1 plus p of -1 plus p of I plus p of -I over 4, this equals a0 plus a4 plus a8 and so on, right? If you just take a look at the sequence, the coefficients repeat every 4 for all of these polynomials. So that means that you can always, everything always cancels out unless it's a multiple of 4, right? I won't go too much into why root of unities filters work so well. That may be another class. But anyways, the useful thing about this is that sometimes it's easy to find what P of I or P of negative I is, right? So like let's look at our coin examples. So what if you have if you flip n coins, what is the probability that you get a multiple of 4 coins? Sorry, multiple of 4 heads. And the generating function would be 1 plus x over 2 to the n, right? Equals sum of over 2 to the n, x to the I, and choose I. And I goes from 0 to n, right? And we want to use our root of unity filter, right? So this would be p of x equals this. And actually, this binomial expansion doesn't actually matter. The nice thing about this is that you can work directly with p. So what is p of 1? P of 1 equals 1, right? Because 1 plus 1 over 2 is 1. And p of negative 1 equals 0. That's easy, right? But then what about p of I? P of I equals 1 plus I over 2 to the n. And fortunately, if you know something about complex numbers, this is actually very easy to compute. Or actually, I don't think you actually need to know anything about complex numbers. You can just compute it anyways. So first of all, let's look for a pattern. So 1 plus I over 2 equals 1. Well, actually, okay, wait, we don't have that much time left, so I'll just like go the quicker example, or the quicker way. So if you graph this on the unit circle, or it's not on the unit circle, just the complex plane, this would be, it would kind of be like the point 1/2 and 1/2, right? The important thing is that the angle equals 45 degrees, right? So that means that 1 plus I over 2 to the eighth power is a real number, and since the norm, right, the norm is root 2 over 2, or like the norm is like the distance from 0 on the complex plane. If you're not familiar, that's totally fine. This equals 1 over 16, 1 over 16. And so, and of course, p of negative I would be the similar. So 1 minus I over 2 to the 8th equals 1 over 16. So we really only need to look at p of I in terms of n mod 8, right? Because every time n increases by 8, we just multiply it by 1 over 16. And that's pretty easy to calculate. And so if you have a specific value of n, you could actually evaluate this term, right? And actually, we want p of I plus p of negative I should be real. And you can actually kind of see this from our old example, or from before, right? Because if you have, remember our 4 polynomials, if you add p of I and p of negative I, well, all the odd terms cancel out, so you don't have any I terms, right? So like these 2 terms cancel out and these 2 terms cancel out. So you no longer have any complex terms, and you're only left with real terms, real numbers. Okay, so we're like basically out of time now, so I'm sorry I didn't get to some of the questions that were in the chat, but I hope you guys learned something about generating functions, and sorry about the technical difficulties, but yeah, this class was mainly just to get any people familiar with everything. There may be homework. It depends on like what people's interests are. I don't think there will be handouts, just because I just wrote a lot, but I will be publishing these slides, and I believe the recording will all be published online on our website. So thank you all for joining. I know it was really short notice, but I will be posting everything on our website so in the coming days. So please keep an eye on the Google Calendar. Oh yeah, thank you for joining. So yeah, see you.